general description of stuff coming up. Again, we've got a lot of miscellaneous holidays. So next week, Monday, for instance, there is no class. There is an assignment that's listed as due Monday. You can do it anytime before then. If you've looked at it, you'll see it is 3 questions long. So I don't think it'll be extremely taxing, but what it does cover is finding critical values of functions, and that's what we've started doing a little bit. We talked about generally talking about what critical values are, which is those places in an accumulation function where the derivative is 0, but the function's defined, or in some special cases, and this doesn't happen nearly as often, places where the original function has something like a corner or a cusp, some sort of point or place where the function exists, but its derivative, its rate of change function, doesn't exist. You could never zoom in and see an approximately constant rate of change. Like the corner, the point of an absolute value function, or lots of others have a single point like that, or sometimes repeated, but those happen in much rarer cases. So in any case, those sorts of points, which could be local maximum or minimum points, they might not be, but locating those potential points of maximums or minimums, tops or bottoms of hills, so local maxes or mins, those points are the x values of those are called critical values, or if we're describing the whole xy point, sometimes it's called a critical point. Sometimes you'll see those phrases used intermittently, or sometimes a critical number of a function. But if you see that word critical, it's talking about, the places where there's a potential to be a maximum or a minimum. And so how we locate those is by looking at the first derivative of a function, or the derivative of whatever it is we're supposed to be finding a critical value for. Figuring out where it would be equal to 0. You can solve equations to do that, figure out where it's undefined. Generally sort of like a find the domain sort of situation. Where is this expression going to be undefined, or where's the end of its domain? So in any case, that assignment that's due Monday, you can probably do some of it now, finish it up this week. It's fairly short. It's just about three questions on finding those critical values, or describing what type they are. And so we're going to spend a little bit more time today on the how do you determine what it is. Obviously, you have graphing capabilities either by hand or with GC or a handheld graphing calculator, and you can look and see something, whether this is a max or a min. But this doesn't make this a useless process, like why are we wasting our time? Why don't we just graph it and look? Just to point some things out, depending on what sort of function you have, how complex it is, you know when you graph something, you can miss some information. Maybe you're zoomed in too close to notice that there's something of interest out farther. Or if you're zoomed out too far, it might appear that the graph is nice and smooth, but if you zoom in closer, you see that there's a lot more detail that you've missed. And sometimes it's just a little blip around a particular value. And so looking strictly at a graph without having done some analytical work, without having looked at what's going on with the derivative, especially if it's a complex function, not something like, oh, that's just a parabola. I know exactly what this shape is. If it's something that you're not sure what all is going on, certainly don't just rely on technology. And also, even if it is something where you know exactly what it's like, rather than having an approximate, like I zoomed in and I put the cursor on the spot on GC and it showed me the XY value, well, maybe the actual exact value is something like 4 over the square root of 3, as opposed to some decimal value like 1.8 or whatever that would come out to be. So instead of having a rounded value, we can find more precise values of where those moments are that the rate of change is essentially 0, or where it's undefined. But in any case, back to where we were at the end of class on Monday. Here we go. We weren't there. We were talking about this g of x function. And we talked about what the shape of this might look like by looking at both its first and second derivatives. So thinking about how you could piece together the shape of the Cartesian graph of function g of x, y equals g of x, we decided that by looking at all these values, we can see that, the as x increases here, my y values go down and then up, and that's all you can see from just looking at the y values. But if you look at the derivative values, you can see that there's this pause here. I've got a graph that's decreasing, pauses for a moment, then increases. So that's definitely that down and back up, or I've got a local minimum. Let me get this going here. We've got a local minimum. happening around x equals 0.5. It's 0.5 comma 1.313 approximately. I think it's 0.3125 actually, if I recall right. But because of this derivative equaling 0 and the sign changing from a negative to a, although we don't write it, a positive, that means my graph shifts from decreasing to increasing. Now, we honestly don't have every single x value here, so just seeing these values on our own doesn't tell us that there's not 7 other points of interest in between, but knowing that this is a 4th degree polynomial and it can at most have 3 turning points, so like down, up, in this case, it's kind of a W-shaped thing at most, would tell us that, yeah, there's not going to be a heck of a lot of other details going on, even without just pulling out a graphing calculator and looking at it. But there's this other 0 of a derivative later, where on either side, and it, a half unit to the left and a full unit to the right, but on either side I've got positive first derivatives. So I've got a low positive first derivative. So I can see this, I've got a flat spot here, which we said was a local minimum, where we know that because the derivative changed from negative to positive, or again, just confirming with a graph, because you'd literally need to determine where are all the zeros of the first derivative, or in other words, where are all these critical values. But just looking at this, I can justify that, oh, this is probably a local minimum, because just to the left, although it is a full half unit to the left, I've got a negative or decreasing function, pausing, and then increasing due to my derivative being negative 0 positive. This is positive 0 positive, which means I would be increasing slowly though, and then flattening out, and then increasing again. So it's not a local maximum or a local minimum. It's just a flat spot, like a ledge or a plateau, however you want to. There's not really a easy word for that. This is called a flat inflection, meaning it's an inflection point in that it's, my graph is changing curvature if I'm looking at it, curved down to curved up, but why this word flat in front indicates that I do have this derivative of 0 in the middle. Not every inflection point has a derivative of 0 at it, just this sort where I pause for a moment and then instead of going down, I go back the direction I started out going. So the other parts you can see, and this is how you can see that the curvature changes, is really from the second derivative. So I was kind of jumping the gun a little bit on that, but if this curvature continued going down, I'd have to have some sort of weird corner spot in reality. But I can see that my graph is curved up and then it flattens out. So a second derivative of 0 just means that the graph is not curved, essentially. So positive tells us about positive curvature or concave up or curved upward. Negative tells us we've got concave down or curved down. So this is curved down between these two flat spots, the one which was our local minimum that we had at x equals 0.5. And then at this point here, we've just got a flat inflection. I'm just going to abbreviate that, Fi. And I can see that both it's very flat, there's no curvature, and my derivative is 0. So lots of inflection points, in fact, all of them, should have a second derivative of 0, because that just indicates no curvature. It's changing from curved up to curved down if it's an inflection point. But also there's other spots that have a second derivative of 0, things that aren't curved. They're just so flat that they have a second derivative. The rate of change is essentially 0 because nothing's moving very quickly at all. So it could even just be something as simple as a parabola, for instance. So if I had f of x is x squared, simplest something I can come up with, the first derivative is 2x, which has a critical value at x equals 0, because x equals 0 makes this derivative 0. So that tells us that the rate of change at x equals 0 is essentially 0, or I've got that pause. We know it's the vertex bottom of a hill. But if I take the second derivative, f prime, oh, sorry, I didn't want x cubed, I wanted x squared, I wanted x cubed. I was talking about that on Friday, or Monday rather, whatever the last day of class was. So I'd have 3x squared, same facts. At x equals 0, this is 0. And the second derivative is 6x, which is also just 0 at x equals 0. And it doesn't mean that that is a maximum or a minimum or something. A first derivative of 0 means I've got this pause. A second derivative of 0 means there isn't curvature or the curvature is changing. Neither of those things tells us necessarily that there's something fancy going on, but if you do have a combination of a first derivative of 0 and a second derivative that's positive, bang, you know you've got something that's curved up and you're at the bottom of it. If you have a first derivative of 0 and a second derivative that's negative, that means you're at a flat spot where it's curved downward. So you must be at the top of a hill of some sort. And same goes for if you have an undefined first derivative, and then you have, if the first derivative is undefined, chances are the second derivative is also going to be undefined. So you'd have to do some more inspection, but you can look for curved up or curved down on either side, even if at the exact point you can't tell what's going on. When you have those undefined points in the derivative, generally it's a lot faster than doing other analysis to just look at the graph or plug in some values just to see what's going on, because there's strange points in a function. But in any case, we have our graph shape then, which if you were to go ahead and graph this on a graphing calculator, I don't have the scale right here, but this graph does go down and then up and then pause and then continue back up. And it's a fourth degree polynomial, so that seems like a reasonable shape. Both ends up from a positive leading coefficient of 1 and goes through 0, 3 because I've got, you know, that constant term of 3, etc. So this should match up with kind of expectations of polynomial graphs that maybe you learned about in earlier classes. But to find these sorts of weird points takes a little bit more than algebra, or you can do this without graphing calculators because we can figure out what's special about those points. Those points where it turns around, those are the places where we've got first derivative of 0. We also have a second derivative of 0 here at a non-flat inflection. This one is the going up. So my graph is increasing, but it stops increasing faster and starts increasing more slowly instead. So the circled one here is my flat inflection. The other one's just a general inflection point. All right, so on to something else then. There we go. So just talking about this, places where the first derivative doesn't exist, you can have corners. You can also have places that aren't corners. So finding that the first derivative doesn't exist doesn't necessarily mean you have a magical, hard to locate max or min. It could just be something like a cube root graph. I believe this is some multiple of negative cube root of x with a shift involved. The rate of change for a moment right here, it was negative, 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 extremely negative, bang, extremely negative to the, you know, undefined at this point, and then becomes normal sorts of negative again. So this sort of graph, and just let me, if we had g of x, ooh, sorry, let me go back. Did not click on something first. There we go. If we had just g of x equals cube root of x, if you remember, that's the same as x to the 1/3 power. Now, cube root of x just looks like this. All right, not quite that graph, but simpler version. If I take the derivative of this, since this is x to the 1/3 power, my result would be 1/3 x to the negative 2/3. So if I were to write that back into radical notation, I've got x in the denominator. It's under a cube root and squared. So I've got x squared under a cube root, which x could be positive or negative in this case because I'm squaring it, and I can take cube roots of either positives or negatives anyway. But what I can't have x be in this spot is 0. If x were 0, this fraction would come out to be undefined. And what that describes is exactly this, that center point of the cube root function, where in this version of it that I have in red here, the graph is increasing all along, sometimes very slowly, but right near the origin, it's increasing. The closer I get to the origin, the larger that number gets, and it exceeds any value you want to pick. I can get closer to the origin so that my steepness or my derivative value is 1,000, a million, a billion. You can get, if you're willing to get close enough, and be whatever large number you want. Or it grows without bound just for a moment. And then it continues growing at a regular sort of pace, and then slows down again. It's because of this x in the denominator, English please this morning, x in the denominator there causes a problem. In the original function it wasn't, so there was no issue with the original function existing at 0, but by the time we've taken the derivative, because of reducing the power by 1 with power rule, we suddenly have denominator factors of x. So in any case, these sorts of situations, like I said, they don't arise a whole lot, and they're generally not the point of interest that we want in cases like this cube root graph. But a corner point or a vertical point are places where the derivative could be undefined, and in the case of this corner point on this absolute value looking graph, that would be our maximum point in this graph, and so that would be of interest. In this cube root related graph, maybe that's of interest if I'm looking for where is the rate at a minimum in this case, or a maximum in the case that I had, at that center point of the graph. But if I'm just looking at for maximums or minimums of the purple curve here, it has nothing to do with that spot there. And that's also, it is an inflection point, strangely enough. It changes from curved down to curved up, so the second derivative changes signs there. But this point in itself isn't going to be something of interest in terms of a maximum or a minimum of the purple function, just of its derivative. So let's take a look at this cubic function. So I'm picking some functions where you maybe have a good idea of what they look like or what sort of qualities they could have, just generally speaking. I've got a cubic polynomial. What we're going to do is figure out where all the critical values of this are, meaning where the first derivative is 0 or undefined. Hint, polynomials don't have any derivatives undefined. And then also places where the second derivative is 0, which would indicate inflection points, or at least really flat spots. So they could be flat, or they could actually turn out to be inflections, depending on if the second derivative changes sign or not. So take a couple minutes. 2 minus 15x plus 9x squared minus x cubed. There should be 2 critical values and 1 spot where the derivative is 0, the second derivative is 0. And then we'll think about what type, if any, of interesting point these are. If it's a maximum, a minimum, a neither, an inflection point, just some really flat spot. And if you want to rearrange the terms, feel free. going to start with the easy half of this. Looking at that second derivative, like, ooh, linear function, that's nice. Maybe even just by inspection on this, you can see, oh, well, the second derivative would be 0 if x equals 3. Okay, so that's when the second derivative is 0, or there's no curvature to the graph of this cubic polynomial. If you think about, well, if it's anything other than 3, it's going to come out differently than 0. So if you think about, well, if I pick a number like 2 or 1 or anything less than 3, this is going to come out positive, right? Which means since j prime prime, the second derivative at 3 is equal to 0. If I evaluate the derivative at something less than 3, I'm going to get something positive as a result. So if I have a number less than 3, my result is something positive, 18 minus something less than 18. Or if I substitute in a number greater than 3, sure, this is formal math notation, function notation with number greater than 3 subbed in. Well, if I sub in anything greater than 3, this will be 18 minus something larger than 18, so I'd get a negative result. Meaning whatever else my function looks like, at x equals 3, the curvature changes from curved upward to curved downward at x equals 3. Right at 3, it's that changing curvature. And if you think about, oh, yeah, this is an x cubed graph. It's got a negative leading coefficient. I expect x cubed graphs like that to generally go downhill from left to right with maybe a bump in the middle. So this sort of fits that. Goes down and then switches around. But it's only got, let's see, it's got one change of curvature, and that's at x equals 3. So the graph may or may not actually go down and back up to get to that inflection point. Maybe it just goes down to that and continues down, more like plain old y equals negative x cubed does. It doesn't have to have two, like a minimum and a maximum sort of spot. But let's take a look at this first derivative and see what's going on. A little bit messier to deal with. I can't just look at this maybe instantly and see what x values make that 0. But I'm going to do a factor out a negative 3 and write this in my favorite order, descending order. I have x squared minus 6x plus 5 is another way to write this. Negative 3 times all of that would be the same as j prime of x's function rule. And what I'm interested in is when that equals 0. So, all right, I can divide by negative 3. That's not the part that's 0. It's this part that has variables in it that's possibly going to be 0. And this should be factorable. X minus 5 and x minus 1. If you want to carry this down, you can, but this part isn't the one that's 0. Only these two could be 0. If x equals 5 or 1, we're going to have a first derivative of function j equal to 0. Meaning an instantaneous rate of change or a rate of change in a moment that's essentially 0 at 2 spots. Well, go back to sort of this idea. Well, it must have 2 flat spots. The one on the right is going to be the 5, and the one on the left is going to be the 1. Here's 3. Nice and evenly spaced here because of the type of terms we have in this polynomial. But also, I could say, well, at x equals 5, I know that substituting in to the second derivative, I get 18 minus 30. So whatever 18 minus 30 is, it's negative. Let's see, negative 12. So the fact that it's negative 12 as opposed to negative 3 or negative 8 isn't going to help you a lot in terms of understanding what's going on, but the fact that it's negative means that, oh, at x equals 5, I've got essentially 0 rate of change. So visually speaking, if you want to picture horizontal tangent line, that's okay. But I also know that my graph is curved down at that point. So I have essentially 0 rate of change right around x equals 5, and my graph is curved downward. So this is what's going on at 5. If I look at what's going on at x equals 1, again, we already discussed this, but you can also do this after the fact. I'd get 18 minus 6, which is positive 12. And again, the 12 part isn't the interesting part. The fact that it's positive is what lets us know that around x equals 1, I've got, again, essentially 0 rate of change, but I've got positive curvature, or concaved up, or curved up to the left of that. And there's only at x equals 3, right in between these, I've got this curvature change. And I know it's a change in curvature because I can see that it's not positive on both sides of 3 or negative on both sides of 3. This expression is positive to the left of 3 and negative to the right of 3, or positive when we're looking at less than 3, negative when we're looking at x greater than 3. So it is a curvature change, not just a 0-second derivative. And so putting all of those pieces together, I can say, oh, well, my function, and you could do this with the first derivative as well. What's going on with this? I've got a 0 derivative. Is it a flat spot or is it a something else? Well, if you substitute in numbers on either side of x equals 1 to this derivative, you're going to see that it changes, to the left of 1, this part's going to be negative, and to the right of 1, this one's going to be positive. This part changes signs. It's in factored form, so that changes the whole signage of this result. You could check lots of different ways, but because we know lots of things about both the derivative and the second derivative, we know that at 1 there's a minimum, at 5 there's a maximum, locally speaking, just meaning higher than the points around it on either side. So altogether our graph would look something like this, where 1, 3, and 5 are this x value locations of a minimum, a maximum, and an inflection point. At that inflection point, I could see the value of my derivative at x equals 3 would be negative 3 times negative 2 times positive 2. So whatever that is, positive 12. So the slope at this point is positive 12. So I also know, oh, it's going uphill when I'm at that inflection point. It's not a flat inflection. It's going uphill, and that's the steepest that this graph becomes in the center there, is a slope of positive 12, or a rate of change of positive 12. So in any case, you can kind of piece together, use in whatever order you want, the first and second derivative facts, as long as you're sure of what they give you. There's not like first you have to do step 1, then you do step 2, then you do step 3. Use all the information, go back and forth between them, just know what each rate of change function, what each derivative is actually telling you. All right, so I did want to talk about just in general some other things that we're going to be doing. In practice, we generally don't have just a function. I want to know where are all the maximums and the minimum spots on this, just for fun. That's useful if you maybe want to draw an accurate graph, but if you're trying to solve a problem, more often than not, you'd like to know how can I make my costs the lowest, or how can I get my fuel efficiency to be the highest? You really only want one of those two sorts of things, and typically also, as a part of that, you're going to have a reasonable domain of your independent variable that's applicable and some values that you wouldn't be concerned about. For instance, with the cubic function we're just dealing with, if we're looking at all the values in the domain of that, which is all real numbers, there is no lowest overall number, and that minimum that we found is kind of irrelevant because there's something as low as, I want to go, negative infinity, likewise with the positives. But if you have a restricted domain, then often there is an overall highest value and a lowest value, as long as your function is continuous throughout that, meaning it takes on all values. There's no vertical asymptotes or whatever in the middle. You will have, on a restricted domain, some point that's the highest, or at least maybe some points that tie for highest, and some point or points that tie for lowest overall. So maximum, absolute maximum and a minimum. So the idea and what we're going to be working on the rest of this class and Friday and Wednesday and possibly Friday next week are about optimization problems in general. So how do I find a specific highest value or lowest value, sometimes given a function to start with, sometimes we have to create it to match a situation that's given. But the idea is that I have a function whose dependent value is the quantity I'm trying to maximize or minimize, depending on the problem. And usually also there's a specific domain that's mentioned. So with any function, there's a variety of different values that maybe I can just investigate what's going on and see what y values pertain. But if I want to know, like, what's the best value of this function, I need to define what's meant by best, like highest or lowest, or maybe it might even be something like steepest, meaning like highest rate of change of something, like when is my revenue growing the fastest, and I have a graph of revenue. I'd actually want to be looking at the derivative of revenue and finding the maximum of that. But regardless, I want to find the best value of something and eventually have a graph potentially of that to assist in managing all the details. But what we get to choose then is how do I, in order to get this best dependent variable value, it depends on having chosen well an independent value. So for instance, the example I said earlier about how do I maximize my fuel efficiency? Well, maybe the independent variable on that is the speed at which you're driving. And so I have to pick the speed to drive that will maximize the dependent variable of that, my fuel efficiency. So whatever the situation might be, we need to know what the function is whose dependent value is the quantity we're trying to maximize or minimize, optimize in general. And then we're also going to need to know what do we mean by best? Is it actually maximum or minimum in the specific situation? And most of the time we also need to be concerned with, also sometimes it just kind of occurs naturally, what's the domain that's relevant here? So in terms of minimizing or maximizing fuel efficiency, we want to maximize fuel efficiency. Who wants to minimize that? And then I might think about the applicable domain. Well, what speeds can I go? Well, I could go 0 through, well, if it's going to be on roads and not getting pulled over, maybe 0 through 70 would be only the speeds in miles per hour that I would consider as a part of this. So in any case, suppose that I'm looking at this function and I just want to consider finding a maximum if the domain is x equals 0 through x equals 30. So 30 is here. So if I'm trying to find the maximum value of this function between 0 and 30, or more specifically, I want to find what independent variable value between 0 and 30 will maximize the output or the dependent variable value. Like, oh, between 0 and 30, looking for the highest value. That looks like that's the highest value that occurs between independent values of 0 and 30. And then I look back and say, oh, well, that happens at around x equals 5. Right, so that's what, so we get to choose what to do with an independent variable value, and that's why it's called independent. And then the dependent happens as a result of that. So whatever this might be, this isn't maybe a very good example to match up with the fuel efficiency, but if we drive 5 miles per hour, we're apparently maximizing our fuel efficiency, and it looks to be about 4 miles per gallon. So just making up a story to go with this, probably not, but the idea is we get to pick one value in order to make the dependent variable, the output, come out to, in this case, we wanted a maximum. So if instead I were looking at 10 through 35 as the domain, like if 5 weren't applicable anymore, like that's not something I want to consider. Only 10 through 35 is reasonable. Maybe it's manufacturing something. I want to maximize my output, but I have to have at least 10 people working. Well, or what's going to, whatever it is I'm trying to maximize profit maybe. I have to have at least 10 people working. So I can't consider this. I'm only going to work from 10 to 35. Oops, I clicked through something else. Hold on. This is, sorry. All right. All right, let me get my other example back. So, quick review. We need to know the function, what's best, and the interval that we're looking at. So, 0 through 30 is one thing. 10 through 35, if I'm only looking at 10 through 35, then 10 to 35, if I'm looking for a maximum, I don't get to include this point anymore. So it looks great, and if you were just doing analysis using derivatives, you would have come up with x equals 5 and x equals this and x equals that as critical values. But if you realize, oh, x equals 5, I can't consider that. That's outside of my domain. I have to have at least 10 people on staff for this, and this is what's happening to my profits. I'd like to only have 5, but I can't do that. Rules about something. There has to be somebody to monitor each section of the process. So if I'm only considering 10 to 35, then, well, that's from here to there on the curve. It looks like the spot at x equals 10 is actually the highest. And there's nothing fancy about the derivative or the second derivative at that spot on the curve. It's just because of how the domain was structured and how that interacted with this function, that happens to be the highest. This looks like the second highest point. But when we introduce the idea of a restricted domain, we come across the idea that, well, it could be actually at the ends of the domain where the highest or lowest dependent variable values occur. Not anything to do with the derivative. It's just that, well, we had to chop off the function there, and it might have been on its way down from something very high, or it might have been on its way up from something very low, or on its way to something very low. So we can find those maximums and minimums not only at critical values of the derivative and places where the derivative's undefined, but also if we have these domain restrictions, sometimes at those endpoints themselves. Again, that's not going to happen all the time, but it's something to keep in mind. If you've created endpoints for your function that weren't there naturally, like they would be at a square root function and you could know something about the derivative at the endpoint, if it's just something artificially created endpoint, then we need to take that into account or think about where those endpoints are relative to the rest of the graph. Are they actually higher than everything else? All right, well, let me clear off this stuff. All right, so if I'm looking at 14 through 24, so here's 14, 24 is here, and I'm looking for a maximum, or up on the graph that's from about here through there. This time it looks like the right endpoint is the highest. There's certainly not anything in the middle that's higher than that. So it could be either endpoint. Now, if I was looking for a minimum instead of a maximum and had this domain, it wouldn't be either endpoint. The minimum, if that were the question, between 14 and 24 would occur at about 16 or 17 or so. So when you're reading a problem description, there's a lot of things to think about carefully, aside from just what's the relationship between the x's and the y's, or what's the dependent variable, independent variable, what's the relationship that I could write down or graph that relates these things. In addition to just what's that overall relationship, what's the applicable domain and what does that mean? And then we can worry about all the calculus stuff. And the calculus stuff, when you get to it, is actually usually the easiest part of it. Like we saw with that J function, that was probably more complex than most of the actual functions you're going to deal with. Most, not all. Some are going to be messy functions. But generally speaking, setting up the problem, reading the problem, understanding what the relationships are, and finally putting together a function that does what you want it to do or models the relationship between the quantity we're trying to maximize or minimize and stuff that we can actually control. Writing that function is usually most of the work of doing what are called these optimization problems. So, as I said, the homework in Math AS that's due this upcoming Monday when we don't have class is 3 questions long. It's just critical values. Here's a function, find the maximums, minimums, and sometimes they are on restricted domains, but the functions are given to you. What we're going to work with now are places where we're not given the functions. We have to work to put those together and then do that. But most of the work is in putting together the function whose max or min we're trying to determine. So I'm going to skip past doing minimums on some of these. All right, we get the idea. So all right, so to find this, because I said some of this already, to find the best value, figure out whether that best value means maximum or minimum. But the places that we're going to look include critical values, places where the derivative is 0, or undefined. If you have a sort of funky function that has weird corner points or endpoints that you're concerned about. Find those critical values. Also look at the starting and ending values, endpoints. So that because if you've created endpoints where there wasn't one previously, it could be that that endpoint or one of them is the highest or the lowest point overall, or does that maximizing or minimizing for you. So every optimization problem has this in common. The overall goal is to have a function that relates the quantity that we're trying to maximize or minimize to some other variable that we can control, an independent variable, and then pick which independent variable value is going to do the maximizing or minimizing. But the picking is usually, as I said, it's the easier part. It's the putting together the function that models the relationship that's the hardest. So here's an example of one that's kind of halfway put together for us. What I mean by that is we were trying to find two non-negative numbers. We'll call them A and B. If it was your own, if it just said it, find two non-negative numbers, then you could use whatever letters you want. But we'll use A and B, whose sum is 25, is another fact about A and B. And we want to maximize the value of this weird expression 2a squared plus b squared. And then we're also going to try to minimize it. All right, so we kind of have a something. We want to be able to maximize the value of this. And then there's this other stuff up here. So even if I called these like x and y, I don't want to, like, I wouldn't want to, this isn't equals 0. This is equals, well, I want it to equal as much as possible. So I could call it y equals 2a squared plus b squared. There's two unknowns in this, though. One of the things that'll make this easier to maybe put together, just as an example, and you can do this with other problems. If you're stuck at what on earth you're supposed to do, I'm supposed to be maximizing the value of 2a squared plus b squared. So first of all, can I substitute in any number I want for a and b? Like, could I put in a as 1 million? No, because, I mean, that'd make a really large value, but it says we have to have two non-negative numbers, and if a is 1 million, a and b have to add to 25, and b is not allowed to be negative. That's not going to work very well, right? So I can't use anything I want. I'd have to, in fact, pick, what's the largest number I could pick for a? Can I pick 25? Yeah, I can pick 25 because b could be 0, right? It just has to be non-negative. 0 is non-negative. So I can't pick 1 million, but I could pick anything for a from 0 to 25. So why don't I just pick 25 for a and 25 for b? That sounds like it's going to make the largest number possible. Well, I can't do that. I mean, I can think about, well, a has to be between 0 and 25. And b does also. But they both can't be 25 because it's not just that they individually have to be less than 25, it's that their sum has to be less than or equal to 25 and there have to be non-negative numbers. So a and b are not independent variables. They're related. They're two things. The fact that we know about them is that their sum is supposed to not just be less than or equal to, but actually supposed to be equal to 25. So if I pick a value for a, there's automatically a value for b that goes with that. So I could pick 0 and 25, 1 and 24, 3 and 22, 10 and 15, and it doesn't actually even say they have to be integers. So I could pick 14.7 and, why did I pick that, 10.3? It could be any sort of numbers between 0 and 25 for one of them, but whatever one of them is, the other one's 25 minus that. All right? So they're not independent of one another, which means that if I want to maximize this expression, it's not actually an expression with two independent variables in it. I could, instead of writing it in terms of a and b, I can express a in terms of b, or I could express b in terms of a. I could rewrite this expression so that it only involves one of the two letters. Like, for instance, a plus b is 25, so b is the same as 25 minus whatever a is, right? And if you're looking at this problem trying to figure out what on earth, how would you know ever to do that, just think about, like, what if I were going to do this via guess and check? I'm going to try to maximize the values of this, and I picked a is 10 and b is, oh, I know what b has to be. B has to be 15. And then I could sub in the value 2 times a squared plus b squared. Or if I picked a is 25, then I'd know I can't just pick whatever I want for b. B would have to be 0, so I'd have 2 times 25 squared plus 0. And so you can kind of see that, oh, well, whenever I pick a, I have to know b automatically by subtraction. So although this may seem like a weird step, it kind of comes from that understanding that a and b aren't just anything you want them to be, they're related to one another. And so if I'm trying to maximize the value of this, or minimize it, either one, I need to understand what the relationship is, and it would be nice if I could have this in a way so that it only involves one independent variable, not two things that are kind of related to one another. So let me say that y is the value of this sum, and then I'm going to graph y against whatever letter I'm left with. But we decided that instead of having 2a squared plus b squared, and I don't have to have a y-axis and an a-axis and a b-axis. A and b are related. I only have to write one of those two. B is the same as 25 minus a. So that means this expression is the same as this, 2a squared plus 25 minus a quantity squared. All right. Well, and if you want to change it for x, you can, but thinking about what's going on with this, I want to graph y against a and find the largest value of y, or smallest to minimize it, that I can. So I want to maximize y, first of all, where y is this sum. I'm supposed to maximize this sum, so I just called it something. I called it y. And I picked y just because thinking about graphs. But there is a domain on this. Even though I only have one letter here, a can only be between 0 and 25. So if a is 0, this part turns into 0, and this part turns into 25 squared. And if a is 25, this part turns into, well, what it did here, and this part turns into 0. But in any case, I can see this to be a quadratic function of sorts in terms of a, so it should definitely have, well, a maximum or a minimum, but I also have, I'm only allowed to use a between 0 and 25. So if you want to think about this graphically, we could expand this. We'd have, let's see, 2a squared plus, let's see, 625, oops, minus 50a plus a squared, or a total of 3a squared minus 50a, putting in this sort of a normal order, plus 625. So I've got this quadratic function that opens upward, goes through 0, 625. The vertex would be at negative b over 2a. Oh, how do I find the vertex of a parabola with calculus? 6a minus 50 is the derivative. The derivative is going to be equal to 0 at that vertex. I know this is a parabola that opens up because I've taken algebra, so I don't have to do a whole bunch of work on this. Like, oh, well, whenever this is 0, that's the vertex of the parabola. And that would happen when 6a is 50, 6a minus 50 equals 0. Or a is, let's see, 50 over 6 is 25 over 3, or 8 1/3 for graphical purposes. Vertex is here. This thing opens up, so I know this is going down, and then it goes way back up there. So just because of, oops, knowledge of parabolas, we don't want negative a values. I know we have a minimum that happens at x equals, or a equals rather, 8 1/3, 25 over 3. And our maximum is going to happen when a is 25, because this y, this dependent value, is the sum that we're supposed to be maximizing. And how I know that this end point's higher than that end point is, well, Knowledge of parabolas. The vertex is closer to the one on the left, so the right end has gotten a chance to go up farther. But you can check in testing when a is 0, when a is 25, and when a is 8 1/3. Notice that this question, what non-negative numbers for a and b maximize this or minimize this? The minimum happens at this vertex, which is a equals 8 1/3, and b equals, well, b is 25 minus that, so that's going to be, 16 2/3? So those add up to 25. And the maximum happens at a equals 25. And that means b is, well, the rest of the 25, nothing. So most of the setup for this was kind of configuring how on earth do I make a function with one independent variable whose dependent quantity is the thing I want to maximize or minimize, and then think about the domain. But once you're past that, this was a quadratic function. We know what quadratic functions look like. This is an upward-facing one. If I find the vertex, I know that's the minimum. It's in our domain. We can even figure out the endpoint. So once you get past the setting it up, most of it's like rolling downhill from then on. It goes pretty quickly. It's the setup that takes a lot of practice, and so that's what we're going to do all class on Friday. I will see you then.